Good afternoon, everyone. Welcome to the first Tutte Colloquium of the spring term. Very happy to introduce Jim Geelen. I think everyone knows Jim Geelen here. He's a professor in our department, and he works on graphs and matroids. As you will see, please, the floor is yours.
Okay, thank you. So today my main goal is to just give a broad introduction to tangles, mostly in graphs, but I'll also talk a little bit about matroids later on. In the second half of the talk, I will mention some new results, and those are with Rutger Campbell. It's a particular pleasure to be giving the talk today in the Tutte Colloquium because yesterday would have been Tutte's 109th birthday if he was still with us. And as you'll see, various preliminary, some of the groundwork for graph connectivity was laid by Tutte that plays an important role in what I'm going to talk about. So I'll be spending most of the talk giving you an introduction into tangles and why we care about them. And hopefully I'll convince you that you care about them. And then after about half an hour, I'll get to the new results. You'll be probably wondering, like, wow, it took him half an hour to explain a tangle. Couldn't he have done it more succinctly? So I'll explain in the next 15 minutes after that how I could have done it more succinctly. And then I'll tell you a bunch of open problems. Okay, so what are tangles? Well, I'm not going to tell you now. I'll tell you in half an hour, but or less. But the basic idea is they're trying to describe k-connected regions of graphs. They were defined by Robertson and Seymour in 1991 in the paper Graph -10. I suspect they would have defined them sooner, but they probably didn't know them sooner because they make a lot of arguments just more elegant when you use tangles instead of other notions. Any of you who know the definition of a tangle, it's probably due to the fact that there's this important theorem in Graph -10 that tangles are dual to branch width. I'm not even going to tell you what branch width is in this talk, but I will define tree width, which is a very closely related parameter. The basic idea is that if a graph doesn't have a tangle of order k, then it decomposes in some nice tree-like fashion, and it's that structure is highly amenable to various proof techniques and algorithmic techniques. So if you don't have a tangle of order k, you can solve pretty much whatever you want to solve. And so now we need to think about the tangles of order k. This theorem to me is, I mean, it's important that there's a qualitative relation. There's a precise relationship which is less important to me. And I think it misrepresents tangles to people. So people think of tangles as being the dual object to branch width, whereas for me, they're k-connected regions, and this is more incidental. As I mentioned before, they use tangles in graph minors a lot, mostly to make arguments elegant. But there is one place in graph minors where you really need tangles. So there's other notions floating around that are qualitatively related to branch width, highly connected sets, brambles, etc. But when you want to prove what the well-quasi-ordering theorem in graph minors, you want to prove that given any infinite set of graphs, one is a minor of another, those techniques fundamentally need tangles. At least I don't know how to prove them without tangles. And I don't know anyone who knows how to prove them without tangles. With all of that said, probably most of us don't spend a lot of time thinking about extreme or structural theory. But tangles are still useful for really concrete problems. I think there's a lot of value to be had for looking at classical theorems in graph theory that involve 4 connectivity or 5 connectivity and relating those ideas and seeing how you can use tangles to prove the same things. I think like revisiting a bunch of the classical literature, talking about low connectivity, but from the lens of tangles, I think is pretty useful. That's on my to-do list. Okay, so let's get started with a sort of general introduction about what a tangle is. So the first thing you do when you encounter graphs is you say, well, I don't really, whatever it is that I'm trying to solve, I can solve separately on the components. So let's just think about connected graphs. And then you work away, and then you're saying, well, actually, what I really care about for this particular problem today is cycles in graphs. So I really want two connectivity, because the cycles will sort of sit on one side of a one vertex cut set. So I can decompose to the blocks. And fortunately, that's unique. I mean, I can just decompose into blocks in an easy way. And then I get the two connected pieces. By the way, I don't impose lower bounds on the number of vertices for connectivity. That's too connected for me, because I can't disconnect it by deleting a vertex. Okay. Right, so that's all easy. And then for talking about decomposing to higher connected pieces, it's convenient to talk about separations. I don't like talking about cut sets. I prefer to talk about separations. So a separation is just a pair of subgraphs that cover your graph. And the vertices that are in both are the boundary. And we're usually thinking of the boundary as being a cut set that's separating stuff in A from stuff in B. However, there's nothing in the definition that says that there is anybody in A that's not in B. I don't care. Usually, often when I'm using it, there will be stuff on either side, but I don't distinguish that. Okay, so the order of separation is just the size of the boundary. And what you can do when you've got a separation is you can just decompose the graph. You put in a bunch of edges in the separation, and then you just pull it apart. And then I can reconstruct my graph by a clique sum, which is just reversing that picture. Okay? And if you keep taking things apart, if I have a separation in one of these pieces, well, maybe I put some of the edges of the clique on the other side, but I can move the edges of this clique so they sit on the same side, right? The vertices all live on one side of any separation because it's a clique. I can't have an edge from there to there. So that clique, all of its vertices will sit on one side, and I can move all of the edges so that they sit on the same side. So I can keep that clique on one side of a separation as I decompose further. And if you do that, when you decompose, you get a natural tree-like structure on the pieces that you've decomposed into. And there's more you can read off from this tree-like structure. So for example, when I see an edge like this, that corresponds to a separation. I just take the union of these pieces and the union of those pieces, and that gives me a separation in the associated graph. So the tree structure, the tree decomposition is keeping a track of all of that information for you. And this is what you get by this clique decomposition. Okay, so now we can return to the task of decomposing. Oh, no, we can't. Tree decompositions come up in various ways in graph theory, and one place you may have seen them is in the definition of tree width. So a graph has tree width at most k if it can be decomposed into pieces, each with at most k plus 1 vertices. Or in other words, the tree width is the minimum k so that you can do this. So here, for example, we have a piece with 8 vertices, and that's the worst you have in this instance, so that graph has tree width at most 7. But it's not the best you can do in this case. I made the mistake of drawing the best thing, and that took me way too long, because that's all I'm going to show you for that. That graph has tree width 3, because I can decompose it into pieces each with at most 4 vertices. Okay, so now let's go back to decomposing into higher connected pieces. So we decomposed into connected pieces and then 2 connected pieces, and now I can take my 2 connected pieces and decompose them into 3 connected pieces. You just keep on decomposing in this way until the pieces are 3 connected. Right, that's just You can just do it. What's nice is that when you do this, you get each piece in the decomposition is a minor of the original graph, which is nice if you're trying to prove something about a minor closed class. And what's more, Tutte proved that the pieces you end up with are uniquely determined. So if you do the decomposition and then I do the decomposition, we're going to get the same set of graphs. Maybe not exactly. There could be parallel edges and stuff we don't quite agree on, but after you remove loops and parallel edges, the graphs we see will all be isomorphic. So whatever you see will be isomorphic to what I see. So these graphs are really intrinsic objects that live within our original graph. Like the pieces I get are somehow fundamental to our original graph because however we decompose, we see the same things. So both of these properties are important. This is more important to sort of tell you, like, this is like a sanity check that, hey, this decomposition is a good idea. The first one's more fundamentally important because if you're dealing with minor closed classes, you want that property. All right, and the basic idea of just decomposing across separations, we saw we could do that in general, and I could just do that for K. I could first decompose into the components, the 2 connected components, the 3 connected pieces, and then I could just work my way up. But both parts of this fail. So if I decompose into 4 connected pieces, it's not true that those pieces will necessarily be isomorphic to minors of my original graph. So think about what happens if you apply this to the Peterson graph. You'll start replacing degree 3 vertices with triangles, and that's not a good idea from the point of view of taking minors. And also, it's not true that if you decompose and I decompose, we'll see the same pieces. You can kind of fix this for 4 connected. You can, instead of decomposing to 4 connected pieces, you can decompose to internally 4 connected pieces and start fixing some of these things. But it gets worse when you go to 5, and then it goes to custard after that. So we're just not going to do it. Going to custard is a bad thing, whether or not you like custard. Okay, so Robertson and Seymour proposed a different idea, that we're not going to decompose. So we'll just try to talk about the K-connected regions without decomposing. So in order to talk about K-connected regions, I need to think about low-order separations, because that's what breaks things up. So I'll let S sub K of G denote all of the separations of order less than K. And now I'm going to use this collection of these separations to talk about what the highly connected regions are. And the basic idea is that if I've got a K-connected region and I've got a low-order separation, then the K-connected region should be mostly on one side of the low-order separation. I shouldn't have a lot of stuff from that K-connected region on one side of a low-order separation and a lot of stuff on the other side, because why am I calling that K-connected then? Right? That would not be a good notion. So there's one side that somehow has most of the K-connected region, and I'm going to call that the big side. So I've got a particular K-connected region in mind, and so I'll talk about the big side and the small side, even though the big side might be physically smaller. I mean, it's like relative to that K-connected region, there's a big side and a small side. So the informal definition of a tangle is the following. I look at each separation of order less than K. So I'm trying to define a tangle of order K. I look at each separation of order less than K, and I declare that one side is big. And then there's a condition that says that you shouldn't be able to cover the graph with 3 small sides. That's maybe a bit of a strange condition, and why 3? Well, 3 is because, I mean, I could have used 4, but 3 works, 4 also works. If you make it 2, a lot of the theory just doesn't work. So it's the smallest number that works. That's why 3. And then if you only take those first 2 conditions, there could be an edge that says, I'm in the big side, always. Right? An edge could just declare itself to be in the big side. That would satisfy the other conditions. That's not very satisfying, so we just say, don't do that. So this is actually, for those of you who know about non-principal ultrafilters, this is, you do exactly the same thing there. That's the non-principal condition. And Diestel has a fair bit to say about the connection between ultrafilters and tangles, and they're closely related. Okay, so you can formalize this. If you remember, my separations are all ordered. Like there's like, when I talk about a separation, I said they were ordered. There was a left and a right. So you're just taking a subset of all separations of order less than k. For every separation of order less than k, one of the 2 things is in the tangle. No 3 small sides cover, and the big side can't contain an edge. Right? That's the formal definition of a tangle. All right, let me talk about an example which might make things a little bit clearer. So, suppose I'm trying to prove a theorem about a graph, and I want to say something about the structure of that graph relative to some Peterson minor. I don't know, I don't have an example, but let's say that's what I'm trying to do. Right, so I've got this graph with the Peterson minor, and then 3 separations in the Peterson minor are kind of nice. It's only basically the neighbors, the edges coming out of a vertex that can really do much. But so if I give you only 3 separation in the Peterson graph, one side's got at most 3 edges. So now if I look at a 3 separation in G, one of the sides is going to contain at most 3 edges from the Peterson minor, because every separation in G induces some separation in the minor. So I can declare the side with at most 3 edges to be the small side, and the other side is the big side. And the Peterson graph's got 15 edges, so I can't possibly cover my graph with 3 small sides now, because I can't even cover the Peterson graph. So that defines a tangle of order 4. And that's kind of nice. I could use that as sort of an alternative to decomposing to some sort of 4-connected graph where the Peterson was in the 4-connected piece, which I probably couldn't do because of degree 3 vertices. I could maybe go do internally 4-connected. But now I could get greedy and say, all right, what if I want a 5-connected sort of region of the graph that contains this Peterson minor? Now, when I look at 4 separations, I can get 5 edges from the Peterson on one side. But I can still define, that still defines a well-defined big side, because the other side's got 10 edges, right? So I can take my graph and I get a well-defined ordering of all of the separations where the small side of every 4 separation has got at most 5 edges from the Peterson. And now I ask, well, is that a tangle of order 5? Maybe it is, but maybe it isn't. So you can cover the Peterson graph with 3 4 separations. Okay, but there's only one way to do that. You have to take 4 vertices with 3 parts each with 5 edges. That's forced. And so if this attempt at being a tangle isn't a tangle, then my graph has a 4-vertex cut set with 3 pieces coming into it with 5 edges from the Peterson in each of them. That's a lot of structure, right? I mean, I've gone very quickly to suddenly saying something quite strong about the structure of the graph that I was looking at. And that's what I got because it failed to be a tangle. It could have been a tangle, so I either get this structure, which I could surely use for whatever it is that I'm trying to prove, or I say, aha, my Peterson graph does define a tangle of order 5, so now I've essentially decomposed to a 5-connected problem. That's useful. Right, so I've managed to push the connectivity up by 1 from 4 to 5 in a fairly cheap way. So that's hopefully convinces you that maybe you can start to use tangles in structure theory for low values of connectivity. All right, here's a really pretty theorem in graph -10. And it's this theorem that says that tangles are really like fundamental to graphs. So the theorem says that you have at most n distinct tangles of order k in an n-vertex graph, and they can be displayed by a tree decomposition. So there's a tree decomposition, and all of the edges in the tree decomposition display separation. So these separations should all be of order at most k minus 1. And there's a tangle associated, so there's a bijection between the tangles and the nodes here. And when I take one of these separations, like this one here, that one of the edges in the tree, it defines a separation. So it's defining this separation, this part of the graph versus this part, right? That gives me a separation. These tangles both say this is the big part, and those tangles say that's the big part. So that's nice. And it's even stronger than that. So if you take two tangles in the tree, like T2 and T5 here, in this case, you see these 3 different separations in this tree. One of those is going to be a minimum order separation separating T2 from T5. So it's going to be a minimum order separation where one of these 3, so this one here, for example, corresponds to a 2 separation. These are both 3 separations. So this one here is going to be the smallest order separation where T5 says this is the big side and T2 says that's the big side. There could be other ones, but one of them is displayed in the tree. This really says that tangles are intrinsic to graphs, right? I mean, there's only n of them. I mean, if you look at things like brambles, which are a dual notion to tree width, there can be exponentially many brambles of any order. If you look at highly connected sets, there could be exponentially many highly connected sets of any order. But here, tangles are really telling you something intrinsic. This is very much like what we saw for Tutte's theorem about decomposing to 3 connected pieces. This is really in the same vein. There's these canonically defined k-connected pieces, but the pieces are tangles, not minors. There's something else that's very nice about tangles, and it's the idea that you can talk about the connectivity of a set of vertices into a tangle. So if you've got a subset, so I fix some set of vertices S in a graph, I can think about the connectivities to that, of any other set of vertices to that. I can talk about that. That's a sort of well-defined thing. And you can do something similar for tangles. But tangles are these amorphous sort of objects, but you can still talk about how connected you are to a tangle in a meaningful way. So what would separate a set of vertices from the tangle? Well, that would be a small separation in the tangle where x is in the small side. Right, that's separating x from the tangle. So what I do is I take the minimum order separation that separates x from the, has x in the small side, so it's separating x from the tangle. I take a minimum order separation separating x from the tangle, and that's the connectivity of x into the tangle. You might not be able to separate x from the tangle, in which case you define its connectivity to be k. It's fully connected into the tangle. And it turns out that this connectivity into the tangle is actually the rank function of a matroid on the vertex set of the graph. Now, of course I like that because I like matroids, but if I take connectivity, if I fix a set of vertices and I take connectivities to a set of vertices, that connectivity is the rank function of a matroid. So what it's saying is that this notion of connectivity behaves a lot like the notion of connectivity that we're familiar with when we've got some target set of vertices. So even though tangles are these amorphous objects, this kind of says that how connected you are to them is a really well-defined concept. Okay, so what underlies all of this machinery, what makes it tick, are the following two properties of separations. So first of all, the order is symmetric, right? I mean, we're just talking about the size of the boundary, so it doesn't matter when I flip it over. And the second property is this submodularity property. If I've got two different separations, I can take the intersection of A and C versus the rest, and that gives me another separation. And I can take the union of B and D versus the rest, and that gives, the intersection of B and D, and that gives me this separation. And the sum of the orders of these two separations is less than or equal to those. So these two properties here underlie a lot of the theory that I've just explained. And you can generalize that theory to other settings where you've got those two properties. So for example, you get those two properties for edge connectivity. If I take a partition of the vertex set into two parts and I count the number of edges between, that's a connectivity function. It's symmetric and submodular. Or if you take the Tutte connectivity in matroids, so the rank of X plus the rank of the complement minus the rank of the matroid, that's another connectivity system. And you can also do a similar thing with mutual information amongst discrete random variables. If I've got some set E of discrete random variables, I can take the entropy of X plus the entropy of the complement minus the entropy of the system. And that tells me some connectivity. Some things don't work exactly as I've described in the previous thing. So for example, the fact that connectivity to the tangle is a matroid would need that the connectivity of a singleton was either 0 or 1, which isn't going to be the case in these situations, but it will be the case in this situation. So again, here you get the tangle matroid. A tangle in a matroid has a tangle matroid. But in these cases, they won't be matroids, they'll be polymatroids. But still, like a lot of what I'm saying works in more general settings. Okay, so now we get to the new results. All right, so what I want to address is the fact that tangles are so big. I mean, for every single separation of order less than or equal to k, I need to tell you which is the big side. That can be an exponentially large set. This is a bit of a disaster. So can I present a tangle to you in a more efficient manner? And more importantly, I think, is like, can I do it in a way that enables you to check which is the big side and which is the small side of a separation? If I give you a separation, I want to know, is it in the tangle or not? Okay, so there's a really nice conjecture about this. Actually, I think Diestel didn't call it a conjecture, but I think he posed it as a question.
Is the decomposition unique, the tangle decomposition?
No, the tangle decomposition isn't unique, and there's all sorts of problems around that because you could imagine like a cycle of things, and you could imagine a bunch of cliques glued together in a cycle. I can't make it really tree-like, but I could just draw it tree-like and just say that's my decomposition. I think trying to really understand that there are versions which people say is a unique version, but they include a colossal amount of other information. If you want to just like have a better version of the tree decomposition, I think we're a long way from that. Okay, so Diestel proposed the idea that you might be able to describe a tangle by just telling me a subset of the vertices, and the big side is the side that contains the majority amongst those vertices. So I count up the number of vertices of Z in B, and I count up the number of vertices of Z in A, and the one with the most vertices is the big side. So if you have a tangle, you can just find this set Z and show it to me, and then that will be the way I decide membership. I just check that property. It's quite appealing. Would clearly answer the questions that I'm going to talk about, but I don't know how to solve this problem. There is a weighted version of this problem. Also, I'm going to call this a tangle decider. I set Z with this property as a tangle decider. So we don't know how to find tangle deciders, but it turns out that you can find weighted tangle deciders. So I can assign weights to the vertices so that the big side is going to be the side with the biggest weight. By that I mean you sum up the weights of the vertices. So I put weights on the vertices and I sum up the weights on both sides, and the bigger one is the big side in the tangle. So any tangle of order K has a weighted decider. So that clearly gives you what I want, right? It tells you which the big side is. I can solve the membership problem. There are a couple of issues there, right? I mean, you need to think about how big these numbers need to be. And I'm embarrassed to say it took me a long time to figure that out. So I only realized this year. I feel a bit embarrassed about it to tell you that, but their paper sets up a linear program with an exponential number of constraints and an exponential number of variables. And that kind of confused me for a long time. I think Jack Edmonds would disown me as his academic grandson if he knew, but eventually I came to the obvious conclusion that the actual definition of what I'm looking for is already a linear program with only linearly many variables. It's got a lot of constraints, but it's only got a linear number of variables, so you definitely can, you get small weights. The weights are at most n factorial or something like that, and that's, when you write that out in binary, it's n log n. So, so this does give you this does give you a nice way to explain tangles to people, and they can solve the membership testing problem. Unfortunately, it doesn't work for matroids. Like, there's a counterexample that this will not work for matroids. So, motivated by this, I sort of revisited the graph problem with Rutger and found a different way that might work for matroids. But it's just a different way of attacking the same problem. Unfortunately, it's a lot more convoluted than, I mean, the weighted decider is quite elegant. This is a lot more combinatorial, and a lot of the parts translate nicely to matroids, but it's more cumbersome. So the way this works is that I start out with taking something that's minor minimal, so that if I basically take a proper minor of my graph G, I lose the tangle, and I'll explain what that means in a moment. And when you're minor minimal, you can cover. So first of all, if I can decide in the minor, the big side, I can use that to figure out the big side in the original thing easily enough. So in the minor, you can cover with 7 small sides. And now we relative to any of those separators, any of those 7 separators, we define an equivalence operation that allows us to change our separation that we're trying to solve the membership problem for. We switch to an equivalent one, which I'll explain in a moment. But the point is that we end up having to solve the problem on a very small number of separators. So we switch to an equivalent one, and there's only 2 to the order k different separators we could end up with after this equivalence. So this is like simplified our problem a lot. And then if you only have singly exponentially many separations, it turns out that you can fix t different separations which will each prove, which like these t different separations that I fix will prove membership for all of the 2 to the t separators. And this is a fairly simple and general technique. So as soon as you get down to only singly exponentially many things, you're in good shape. Okay, so first of all I need to talk about what I mean by minor minimal. And we kind of saw this earlier, right? So I talked about the Peterson graph, and the Peterson graph has a tangle of order 4, and we use that to define a tangle of order 4, and anything that contains the Peterson graph is a minor. So if I give you a tangle in a minor, it induces a tangle in the big thing, in the same way that I did with the Peterson. And if I can test membership in the minor, I can use that to test membership in the big thing. So if I could take a minor in any way and have a tangle in the minor that induces my original tangle, great. And so I'll say that G is minor minimal for the tangle if, however I take a minor, I don't have a tangle in the minor that induces the original tangle. There might be tangles of order k, but they don't induce that tangle that I care about. And so for the membership problem, I can assume that G is minor minimal for the tangle. And if you're minor minimal for a tangle, then there are 7 different separators in the tangle that cover the graph. You can cover with 7 small sides. Rutger and I proved that recently, but I'm pretty sure that somebody told me that 20 years ago. I wish I could remember who, but I think I've known that for a long time. And I think if you mention this to anybody who works a lot with tangles, they'll go, oh yeah, that's true. Okay, so what we're going to do is we're going to look at these 7 different separators in our cover, and we can just, let's fix one of them and think about the membership problem relative to that. So remember, you can't cover a tangle with 3 small sides. So if you give me 2 separators, 2 different separations that look the same on B and only change on the small side, only differ on the small side, then those 2 separations have to either both be in the tangle or neither be in the tangle, because, I mean, if one of them said that this part's small, no one says this part's small, regardless of what's going on down here, this is covered by A, which is small, and I've covered by 3 small sets. So if 2 different separations agree up here, then they agree which the big side is up there. Like, now, what I can do is, so you give me this separation CD, and I'm trying to figure out whether it's in the tangle or not. I can replace it with anything I want down here, so I may as well take a minimum cut separating these 2 blue parts. Might as well take a minimum separator separating the 2 blue things. That's just a connectivity problem I can solve. So replace CD with the minimum separator on this side. And while I'm at it, let's make it leftmost. So that's uniquely defined now. Like there's a unique leftmost minimum separator separating those two parts. And so then I'll say that separation that I changed it to is the leftmost one with respect to AB. Now, there could be, so I could have started with a lot of different separations, but what I see down in A after I move to the leftmost one, I won't be able to see very many different things. So I take all the different K separations in the K-1 separations in the graph, and I do this. How many different partitions am I going to see down here? Well, there's only K-1 vertices in the boundary. They get partitioned into 3 sets, so I don't really care what's going on up here. These get partitioned into 3 sets, and I'm solving a connectivity problem between these 2 sets and these 2 sets down there. And so the number of different things, different ways I'm going to partition down here is at most 3 to the K. Okay, so the number of different, after I take all the different separations in the graph and I look at the leftmost ones down here, I'm going to see 3 to the K different things. But now if I take my separation leftmost with respect to everybody in the cover, the bottom parts cover the graph, and so I'm going to see at most 3 to the K to the power of 7. So I'll see at most 3 to the 7K things, which is less than 2 to the 12K. So the number of leftmost separators that are leftmost with respect to the whole cover is at most 2 to the 12K. Now, annoying things can happen. Like I can take a separator that's leftmost with respect to the first one, and then I can apply the second one, and I can take it leftmost, and then it may not be leftmost anymore with respect to the first one. But every time I do this, I either make the order of the separation smaller, or I make the left side smaller. So it won't take me long to find something that's leftmost with respect to all of them. And there's not very many separators that are leftmost with respect to all of them. So no matter what I started with when I asked the original, doesn't matter which separation I started with when I asked the question, I'll end up with one of at most 2 to the 12K different separations. Okay. So now I want to describe the tangle. I look at all those leftmost separators, call that script S. So let's just take the ones that are in the tangle, right? Because I'm trying to decide which ones are in the tangle. So let's just take the ones that are in the tangle. Let's take the leftmost separators that are in the tangle. For each of these separators, what I'm going to do is push the separation rightmost now in the tangle. So basically what I'm doing is I'm taking the closure in the tangle matroid of the vertex set of the left side. Essentially, that's what I'm doing. So I'm going to call the separators that I get by doing this the closure of the original ones. So now my tangle is described by, I've got a description of the tangle just in terms of the original cover and these closed separators. Unfortunately, there's still a lot of these closed separators. We've got like 2 to the 12K, which is not ideal. I'm going to skim through the next thing because I really want to get to open problems. But basically, I can choose one separator in the closed set that I can use to prove membership for at least half of the other ones. And basically, the idea is just this. I look at these two connectivities. So if I take two different closed ones and I look at these connectivities, by submodularity, I get one of these two formulas, and the one that holds will tell me which one I want out of the two. This gives me a tournament, and there's a vertex of degree at least half in the tournament, right? I mean, that's how I get this. And you just need to think a little bit to to see why that can be used to force membership in the tangle, but nothing's complicated there. Okay, so I'll skim over that and just say that the only part where we really used graphs was the fact that I took the k-1 vertices and I partitioned them into 3 parts. That's the only thing that was talking about graphs as opposed to submodularity and things like that. So, the minimality things are really about connectivity systems as long as you've got appropriate notions of minors. All right, open problems. Obviously, Diestel's problem is still open. And so one question you might ask is, can we at least find better weighted deciders? So can I find things where the numbers are little o, big O1 or big O of n, something like that. Here's a greedy algorithm that might work. So this is going to give real numbers, but they're quite nice real numbers. So I start by defining all the weights to be 0, and then I uniformly increase them. But I want that for every separation in the tangle, I want the weight of the small side to be at most the order of the separation for all of the separations in the tangle. So as soon as one of them hits the bounds, so as soon as I get equality, I'm going to freeze the weights on the small side and then keep uniformly increasing the rest of the weights. If, when I'm finished, the sum of the weights is more than 2 times k minus 1, then the big side will always be bigger than the small side because of the separator order k minus 1, right? So if I ever get this, the small side I've forced to be less than the order of the separation, which is k minus 1. The sum of the weights in the small side is always less than or equal to k minus 1. So here the big side will always be bigger than that. And I conjecture that that will always work. So that gives you a conjecture that that will give you a weighted decider, and those numbers will be nicer than the ones you get out of the linear programming. Another thing I'd really like is, if I give you a separator, I can tell you which is the big side of it. That's the membership problem. But to use a tangle in a meaningful way, what you really want to do is to be able to compute the connectivity into the tangle. And so I don't know how to do that efficiently. So I'd be curious if you could do that efficiently. I strongly suspect you can. I don't even know how to do that efficiently, even if you give me a decider. So even if I'm lucky enough to have a connectivity system that's described by a decider, I don't know how to compute the connectivity efficiently. Another thing I'd really like to prove is that tangle matroids for graphs are representable. I would be shocked if the answer was no, and I think they should be representable in all characteristics. We understand connectivity to a given set fairly well. These are basically gamoids. These things shouldn't be very different from gamoids, and gamoids have nice constructions. So it would be nice if we could understand these in terms of standard matroid constructions. And I think that's a reasonable thing to want, I just don't know how to do it. Another thing I believe is that if you look at a graph that's minor minimal for a tangle, then the number of vertices is at most k squared. K squared comes from a grid. And then you don't need pretty much anything from what we talked about before, because we had this way of taking a singly exponential number of separators and deciding them by only linearly many things. So here we'll end up with a bit more than that, but here we'll get a polynomial number of things, right? So if I get a polynomial here, I can get a polynomial there. That would be very nice. We can prove a bound of something like 6 to the k, but that's not going to help us here. Okay, for matroids. So we would like to be able to do the same kinds of things for matroids. So can we solve the membership problem efficiently? I suspect yes. And again, I'm not at all, this is more like wishful thinking than a conjecture, but still, if M is minor minimal for if I take a matroid that's minor minimal for a tangle, I conjecture that the number of elements is bounded by some polynomial in K. Again, I don't have a lot of faith in this, but if this was true, then exactly what I said for the graphs also holds, that this would give you an efficient way to test membership using exactly the same machinery that we had in the previous part. And just as with, for graphs, I would be shocked if it's not true. So if I take a tangle matroid of a tangle in a representable matroid, I expect that to be representable and also in the same characteristics. So basically over an extension field. I would expect that to be true, and I would expect to learn that by understanding how to construct these things. But I don't know those constructions, and it seems fairly hard to approach any other way than learning how to construct them from basic matroid operations. Okay, I also mentioned that deciders don't work for tangles in matroids, and you don't even get weighted deciders. And the reason for you don't get weighted deciders is the example that shows you that things don't work for deciders is a very rich automorphism group that also respects the tangle. So if you had a weighted decider, you could apply all the different automorphisms and then add them up, add up the deciders and get a uniform decider, right? So this is like, so that doesn't work. So what do I mean by deciders don't work? I mean, if you choose a subset of the elements in the matroid, so what's your decider? You choose a subset of the elements in the matroid, you look at a separator, and you take the big side to be the one that contains most of the elements, right? That's the natural way to talk about a decider. That's the most obvious thing to do. Maybe the most obvious thing to do isn't the right thing to do. So maybe if you give me a tangle of order K in a matroid, I can choose a subset of the elements with the property that the local connectivity from that set to B is more than the local connectivity from that set to A for every separation in the tangle. So here the local connectivity between two sets is the rank of X plus the rank of Y minus the rank of X union Y. So in a represented matroid, it says, this is saying take the subspace spanned by X and the subspace spanned by Y and look at the dimension of their intersections. This is actually not too far from what you're doing in graphs, right? This is actually a fairly sensible interpretation of what deciders should be, and maybe this works. I'm not that confident. As you see, I put the word question there, not conjecture. For a binary matroid, I would change it to conjecture if you did the following. Think of your binary matroid as a set of points in a projective space. Don't choose Z from your matroid. Choose them from the projective space. And then do that. And then I'd be willing to put conjecture there. But that's because I write conjectures pretty easily. I don't have massive faith in that, but it seems pretty plausible that's reasonable. That's a reasonable thing to do. And more generally, you could take a matroid and ask, can I extend the matroid in such by some set Z in such a way that when I look at separators before I added the elements, they're decided by this local connectivity after I added the elements. I won't write that down concretely, but I'll stop there. Thanks.
Thank you. If there's any questions, please wait for the mic. For the
Steve?
It's probably, yeah. So, sorry, so you spoke about deciders, and in graphs you had this weighted functions, and then you compared which side has larger weight. So I guess, yeah, I don't get the intuition, but I was wondering if you have, okay, so this was linear function, but what happens if you have something like more like polynomial? Let us say you have low degree polynomial. Is there a hope for some classes of matroids to have deciders that are not maybe like degree 1 polynomial, so you just, but degree 2, degree 3, which you also can encode compactly?
How would I be, how would I define it?
So then you will plug in 0, 1 vector that is characteristic vector of your side, and then you evaluate the polynomial then on characteristic vector on one side and on characteristic vector on another side. So this will be like what one you would do for linear.
Yeah, okay. Right. Would be a sensible thing to try. I don't know.
Thanks.
You pose a bunch of things with like algorithmic implications. Is there like some hardness results like that you like known about like, oh, like there's this tangle that having a decider would be, you know, too strong, or like what is known about like what on the hardness side and what can be done?
There are some negative results towards like being able to compute rank in tangles under the oracle model. You can just say that in certain, like you can't do it always because like, but that's only under this oracle model. Because you can do things like I can give you a matroid and you can't know ahead of time whether it, like you, I can't distinguish a uniform matroid from a matroid with just a small number of dependent hyperplanes with an oracle. And so there are things like that you can do just to say to get negative results. So I don't know any other seriously negative results like just with normal complexity assumptions. Yeah, I probably should look up that because there probably are some negative things. There's certainly negative things for tree width. I don't know, like I think people haven't proved them for branch width. I don't think people like don't know much about their complexity.
If there's no more questions, then let's thank Jim again.